This is the last video in the chapter about gases and gas laws. This one is about non-ideal gas behavior, an important caveat to our ideal situation. The main points in this video are about the ideal conditions and about the van der Waals equation. So everything we've talked about so far about the pressure and the volume and the relationship between them and the qualitative explanations and the quantitative explanations for the velocity, all of this holds fairly well true for gases under ideal conditions, much more so than any sort of a model for liquids or solids. But we have to acknowledge that for every theory, there is a flaw. There are conditions when that theory does not hold true anymore. So let's talk specifically about when those are. So the ideal conditions where the behavior that we've talked about and modeled happen most accurately occur at high temperature and low pressure. This is pretty similar to wherever you are currently sitting right now, where the temperature is probably in the 70s and the pressure is 1 to 1.5 atmospheres. In a situation like this, the gas particles are going to be fairly spread out in their container at low pressure, and they're going to be moving very quickly in the container. So they are fast and they are spread out. So this is when you have the two first graders and they're at opposite ends of the football field. They're running around very, very quickly and they're very, very spread out. So it's unlikely that they're going to run into each other in the container and cause any problems. But not every gas exists at ideal conditions. Conditions change after all. Example A, space. Space is at a very, very low temperature, and the gases are much more difficult to model there because they don't fit within this nice box of ideal conditions that we've drawn. So non-ideal conditions include gases at low temperature and at high pressure. So let's think about what would make a gas difficult to model with our current theory at these types of conditions. So let's draw our picture again. So our gas molecules are in this same box, but this time it's at high pressure. So that means there's a lot more particles shoved into the box, like trying to fit 47 first graders into one small classroom. And they're at low temperature, so they're moving a lot more slowly. Maybe it's right after nap time. So we've got slow moving particles and a very crowded space. And let's think about those assumptions we made in the video on kinetic molecular theory. We said those gas particles are very small. They're much smaller than the gaps between them and the next particle. And we can see here that that's not true. These particles are very crowded together in the container. We said that the particles were moving, excuse me, quickly and in straight lines, and that's not exactly true. And we said that the particles don't interact with one another. Their collisions are elastic. And as we know, when you fit 47 first graders in one room, they are definitely interacting with each other. They are grabbing each other, they are punching each other. Adjustments will have to be made. So let's look back at the assumptions from kinetic molecular theory and figure out which assumptions we've broken with this non-ideal box. So here's our assumptions. So I'm looking at number 2 here. So we said that gas molecules are separated by great distances and the gas is mostly empty space. And I'm going to say in the non-ideal picture, that is not true anymore. So in the non-ideal condition, the molecules are so crowded together that the volume of individual particles becomes significant. And that was assumption number 2. So before we could say, oh, well, the particles are super small and they're super far apart, so the volume that they take up in the container doesn't really matter. But in this case, there are so many particles in such a small space that the volume that they take up does matter. It does matter to our model. So let's go back to the assumptions. Let's see, extremely small is still true. Colliding into the walls makes pressure, that's still true. Number 4 says there are no attractive or repulsive forces, and that is going to be different when the particles are very crowded together. And this has to do with the crowding and with the speed. So the molecules are moving very slowly at a low temperature, and it's so slow that the attractive and the repulsive forces are going to be significant. And I don't want you to think that the attractive and repulsive forces were never there, because they are there. But what's different here is the speed at which they're moving and how closely that's related to this force. So I have an analogy for you, and that is why the speed is important to noticing these forces. So my analogy is that if I am driving in my car, how likely am I to notice a Dairy Queen by the side of the road because ice cream is my favorite thing? If I was in an ideal condition and I was moving very quickly, I was driving on the highway and I saw it on the side of the road next to the exit, there probably won't be enough time for me to notice the ice cream because I'm moving much, much faster. And there wouldn't be time and I would miss the exit and I would end up just continuing along my way. But under non-ideal conditions, if I was driving through town and I was moving slowly past the Dairy Queen, there's much more time available for me to notice the Dairy Queen and swerve off course to get an ice cream before continuing on my way home. And my husband would want to know why I ended up at home so late and wasn't hungry for dinner. And so that's the same thing for the attractive and repulsive forces. The attractive and repulsive forces, just like the Dairy Queen, were always there, but they're only noticed, they're only significant when the speed of the molecule is slow enough that it can be affected by them. So when the molecules are moving very slowly at low temperature, they're more susceptible to these attractive and repulsive forces as they move by other molecules in the container. And there are more molecules available for them to run into. So this is like if there was a Dairy Queen every other block on the way home, it's much more likely that I would run into them. So in summary, there are occasionally some issues with our ideal theory under these non-ideal conditions. So a series of scientists have made adjustments to the ideal gas law, trying to make it more accurate for these non-ideal conditions. So the ideal gas law needs improvements. So one of these improvements on the formula is called the van der Waals equation. This is one of the simpler ones, so it's appropriate to talk about here in class, and it's relevant to these assumptions of the kinetic molecular theory that we noticed it breaking. So here's our ideal gas law as normal. PV equals nRT. That is our ideal gas law. And we want to make adjustments to a couple of the factors to adjust for these two issues that we are seeing. So we need to make an adjustment for this attractive repulsive force, and we're going to make that adjustment to the pressure term. So we're going to add in this adjustment factor here, AN squared over V squared, to this one. And then for this significant volume of the particles, we're going to make an adjustment to the volume factor. So we're going to add this NB adjustment. So those two, the pressure and the volume, are going to get an adjustment, and the nRT part is going to stay the same. So this is our van der Waals equation. Okay, so first of all, we have these adjustment factors. So right here, this is our first adjustment factor. This one adjusts for the attractive forces. And it also starts with an A. Brilliant. And this guy, technically including the negative sign, that adjusts for the non-zero volume of the gas. And you'll see that there are some new variables that have been added. So there's this A right here, and there is B right here, and those are not variables we know. So those are new constants. And those constants are listed in reference tables, and you can look them up for a particular gas at a particular temperature if you're looking to use this formula on your own. So we can make adjustments to these formulas with these additional variables and these additional terms. And the important part here is, as you can see, these are similar. This van der Waals equation is a slightly more complicated version of the ideal gas law. And so if we are able to reach ideal conditions, we can make these adjustments factors cancel to simplify the equation back to the original. So we can do that under ideal conditions when the number of moles is small and when the volume is large. When those are true, these adjustment factors in the van der Waals equation, those become very, very small or negligible. Hold on, negligible. And we can disregard them. And that means that the van der Waals equation reduces back down to the ideal gas law. So let's look at those conditions. When the number of moles is small and the volume is large, that's what our ideal picture looked like. There was a very large amount of space for a very small number of particles. They had plenty of space to spread out and move around without running into each other. That's our ideal conditions. And if we look at how that affects the formula, over here, for the volume adjustment, if n becomes very small, this number will go to 0, and it will disappear and just become a v. And for this term over here, if n becomes very small and v becomes very large, then this term is going to go to 0, and it reduces down to p. So we can use math to indicate when the conditions become ideal again, and that simplifies one formula back into the original. So it's not appropriate to talk about a theory without talking about its limitations. So the limitations for the ideal gas law occur in low temperature, high pressure situations. And you've made it to the end of the gas law chapter.